Hello friends, I'm Zishan, an auditor at Quantstamp, and today we'll be talking about the largest smart contract hacks in March. Now, March of 2023 saw over $213 million of assets lost due to hacks in Web3. This is much higher than February, which only saw about $35 million lost. Now, of this $213 million, over $160 million was either returned or rescued. The largest hack in 2023 so far happened on the Euler Finance protocol. Now, Euler Finance is an over-collateralized Ethereum-based lending protocol. Over-collateralized simply means that the amount we borrow from the protocol must be less than the amount of collateral we provide. Users can become liquidity providers in Euler Finance by depositing their assets into Euler's liquidity pools. And when users deposit these assets, they will receive E-tokens. E-tokens are the LP tokens for Euler Finance. And when users borrow assets from Euler Finance, they receive D tokens or debt tokens. The protocol was exploited on March 13th through a vulnerable donation mechanism. This exploit resulted in a loss of $197 million worth of funds. As mentioned before, the LP token of Euler Finance is the E-token. And the E-token features many functions that a user can call in order to interact with the protocol. One such function is the deposit function. Users can call deposit in order to deposit their assets in exchange for E-tokens. Users can then redeem their E-tokens by calling the withdraw function to get the underlying asset which they originally deposited. Users can also leverage their position by using the mint function. Users can repay D-token liability as well by using E-tokens when they call the burn function. Now, all of these functions that we just mentioned require a liquidity check, and the liquidity check must pass. The liquidity check is shown here below and basically ensures that the position's collateral value is greater than the debt or the liability value. This ensures that the position is still over-collateralized. It also relates to the health factor of Euler Finance. Now, the health factor in Euler Finance is defined by the collateral value divided by liability or debt value. This means that the health factor should generally be above 1. This is because the collateral value should always be higher than the liability or the debt value. However, if the health factor drops to a dangerous level, Euler Finance allows liquidation. And there are two types of liquidation offered by Euler Finance. The first one is soft liquidation. Soft liquidation allows for liquidation when the health factor is in between 1 and 1.25. Then we have the standard liquidation, which happens when the health factor is less than 1. When this is triggered, a Dutch auction is activated for purchasing collateral. Euler Finance incentivizes liquidation by offering discounted collateral, and this discount can be as large as 20%. So as you can imagine, liquidation can be quite a profitable activity in Euler Finance. Here's an example to demonstrate this. Let's suppose Alice has a position in Euler Finance, and this position has $800 worth of collateral and $1,000 worth of debt. Now, this position is underwater because there is less collateral than debt. And so Bob is able to liquidate Alice's position with the 20% discount. This means that Bob is able to obtain the $800 worth of collateral with that 20% discount, and so it's a very favorable action for Bob. The root cause of this hack was the vulnerable donation design mechanism, and so this took the form of the donate to reserves function, which was introduced in August of 2022, just 8 months before the hack. The intention was for this function to allow users to donate dust to the Euler reserves. However, this function created a vulnerability because it allowed the burning of E-tokens and non-D tokens, and the function also lacked a liquidity check. So the combination of these two factors allowed the donate to reserves function to be used to make the health factor go lower than 1. We've already established that liquidation is quite a profitable activity in Euler Finance, and so we can come up with this invariant. The invariant is that no protocol action should result in a liquidatable account. If this was possible, that someone could immediately liquidate this account and make a profit at the expense of the protocol. So most functions in the E-token contract do enforce this invariant through the liquidity check. However, the donate to reserves function does not have this liquidity check, and so the health factor can go below 1 when calling this function. Let's have a look at an example which shows just how the use of this function can cause a liquidatable position. Let's suppose that a user deposits 210 million USDC into the Euler Finance protocol. At this point, the user receives 204 million EUSDC, but they have 0 DUSDC because they haven't taken on any debt yet. Then the user calls the mint function in order to leverage their position. So this results in the minting of both EUSDC and DUSDC. At this point, the health factor is still above 1 because the collateral represented by this EUSDC is still supporting the debt represented by this DUSDC. However, it all changes when the user donates a massive amount of EUSDC to the Euler reserves. When this happens, the user's balance of EUSDC drops significantly. And in fact, this balance of EUSDC does no longer support the debt over here represented by this DUSDC. And so the liquidator can immediately liquidate this position while receiving that 20% discount. Let's review each step of this hack. Now, the attacker actually deployed 2 attack contracts. The first attack contract was the violator, and the purpose of the violator was to create an unhealthy position in Euler Finance. The other attack contract was the liquidator, and the purpose of the liquidator contract was to liquidate the violator's unhealthy position. So the violator starts by initiating a flash loan for 210 million USDC. Some of this USDC is then deposited into Euler Finance to retrieve some EUSDC tokens. The violator then calls the mint function in order to leverage the position and mint both EUSDC and DUSDC. Part of the loan is then repaid, and then the violator calls the mint function again to further leverage the position. At this point, we have more EUSDC tokens and more DUSDC tokens. At this point, the health factor is still above 1 because the collateral represented by this EUSDC still supports the debt represented by the DUSDC. This changes in step 6 here, where the violator donates 700 million EUSDC tokens to the Euler reserves. This causes the health factor to drop below 1 because the collateral represented by this EUSDC no longer supports the large amount of debt here represented by the DUSDC. At this point, the position is liquidatable, and so the liquidator contract is able to liquidate the violator's position with that 20% discount for the collateral. The liquidator then withdraws what they got from the liquidation, pays back the flash loan, and makes a profit of 34 million. They repeat the sequence of steps until the entire protocol has been drained of funds. Now, Euler was integrated with many other protocols within the DeFi ecosystem, and all these protocols were impacted because they may have been using Euler Finance's e-token or integrated with Euler Finance in some other way. The attack was identified on-chain within 10 minutes of it occurring, and an hour later, Euler acknowledged the hack and said they were working with security professionals and law enforcement in order to track down the hacker and determine the root cause of the hack. 2 hours later, the Euler team tweeted that they had disabled the vulnerable e-token module, which contained the vulnerable donation mechanism. 2 days after the hack, Euler announced a $1 million bounty for information leading to the arrest of the hacker and the return of the stolen funds. Now, there was an extensive on-chain conversation that happened between Euler Finance and the hacker. Euler initiated this conversation by inviting the hacker to discuss the potential return of funds. When the hacker didn't respond, Euler sent a more threatening message to the hacker, warning them about the $1 million bug bounty leading to the arrest for information leading to the arrest of the hacker and the return of the funds. Nothing happened for 1 week, and then the story took on an interesting twist. The Ronin bridge hacker actually tried to manipulate the Euler hacker into decrypting a message with a vulnerable library. And the Euler team immediately detected this and warned the Euler hacker not to do this. And presumably this was so that the possibility of recovering the funds from the Euler hacker remained. The Euler hacker later indicated some willingness to return the funds. 1 week later, the pressure on the hacker mounted, and they indicated a more definite willingness to return the funds. Finally, they expressed regret and did return all the funds to Euler Finance. The root cause of the hack was the donation mechanism, and in particular, the donation function was lacking the liquidity check. It may have seemed as though the donation function did not require this liquidity check because the donation mechanism in itself doesn't lead to a profit. However, when combined with the liquidation mechanism, donation actually does become profitable, as we saw in this exploit. Also, the original intention of the donate to reserves function was to allow the donation of dust from users to the Euler reserves. However, in the case of this exploit, far more than what could be considered dust was donated to the Euler reserves. In fact, 700 million EUSDC tokens at least were donated to the Euler reserves. Now, the code for Euler Finance was manually reviewed, however, the vulnerability was not detected. And this can be because some bugs are difficult to detect using manual review, and manual review in these cases should be supplemented with techniques such as automated code analysis and fuzzing. In particular, a fuzzing campaign or using a tool such as FlashSpin would have detected the sequence of actions leading up to this hack. Let's move on to the second largest hack in March. This happened on the Safemoon token. Now, Safemoon is a fee-on transfer token deployed on Ethereum, Binance Smart Chain, and Polygon. And a key part of the Safemoon functionality is this transfer fee. Part of the transfer fee is burned, some of it is distributed to existing holders, and the remaining components are either set to the DEX to provide additional liquidity or to the ecosystem fund. The team behind Safemoon also developed its own DEX called Safemoon Swap, which would be exploited within this hack. Now, the Safemoon contract, this is the token contract, was actually upgraded on March 28th, and just 6 hours after this upgrade, Safemoon Swap's Safemoon BNB pool was drained of $8.9 million worth of BNB. The root cause of this vulnerability was a publicly accessible burn function that was introduced in the token upgrade. Just to show you that this burn function can be accessible by anyone, let's have a look at the mint function. The mint function has this access control modifier called onlyWhitelistMint. This ensures that only whitelisted addresses can mint tokens. However, no such modifier is present on the burn function. And so this burn function allows any user to burn anyone else's token in any amount. So how does the attacker use this? How does the attacker use the burning of tokens in order to make a profit? The attacker actually burned the tokens not from a user, but from the DEX pool containing Safemoon and BNB. And so most of the Safemoon in the DEX pool was burned, leaving very little inside. However, the BNB balance of the pool stayed the same. So it looked as if the small amount of Safemoon left in the DEX pool was worth all of that BNB which was originally there in the DEX pool. And this allowed the hacker to make a swap from Safemoon to BNB and drain almost all the BNB liquidity. The first step of this hack was for the attacker to take a flash loan for PancakeSwap. They borrowed about 1,000 BNB for PancakeSwap. The attacker then swapped this 1,000 BNB for Safemoon using the Safemoon swap pool. The attacker then burns a large amount of Safemoon tokens from the Safemoon BNB pool. At this point, there's very little Safemoon left in the pool, but the balance of BNB remains the same. They then call the sync function of the Safemoon swap pool in order to force update the reserve numbers. And the reserve for Safemoon now becomes a very small value because it matches the balance of Safemoon within the contract. However, the reserve of BNB remains the same as the balance of B did not change. And so at this point, the DEX pool has very little Safemoon and a lot of BNB, so it makes it look like the Safemoon is worth a lot of BNB, which it in fact is not. The attacker then uses all the Safemoon they accumulated in step 2 over here and swaps it for BNB in the final step of the hack. And because the Safemoon seems so valuable in the DEX pool, because there's only a little bit of it, they're essentially able to extract most of the BNB from the pool over here. Now, users raised the alarm in Discord 8 minutes after the exploit, and the team actually identified the root cause and patched the vulnerability within 4 hours of the exploit. The hacker sent an on-chain message to the team claiming that they accidentally had front-run another attack. However, looking at the on-chain activity of this hacker, this seems doubtful as they seem to have been responsible for other exploits as well. We didn't hear anything about the hacker for 3 weeks after the exploit, but finally it was revealed that the hacker agreed to return 80% of the funds in exchange for a 20% bug bounty. The best way to prevent vulnerabilities like these is through thorough access control testing on all privilege functions. Basically, there should be tests to ensure that the privilege function should not be accessible by an unauthorized address. So in this case, presumably the burn function was only meant to be accessed by certain privileged addresses, and so it shouldn't have been accessible by the attacker. Also, the original version of Safemoon was audited. However, this upgraded and updated version was not audited, and it's very likely that an audit would have detected this vulnerability. Generally speaking, it seems to be a trend among protocols that contract upgrades are not treated with the same level of caution as the original contract deployment. And unfortunately, this leads to many bugs being introduced during upgrades, and these bugs can lead to exploits, as in this case. Another important security incident which happened in March was the attempted exploit of ParaSpace. Now, ParaSpace is a lending protocol on Ethereum which allows users to borrow against both ERC20 and NFT collateral. ParaSpace supports many well-known NFT collections as collateral, including BAYC, CryptoPunks, Azuki, and many more. Another important feature of ParaSpace is that it features maximally effective and auto-compounding ApeCoin staking. This solves a problem for some BAYC holders which don't have sufficient ApeCoin to get the maximum staking rewards. Now, on March 17th, a security firm rescued approximately $5 million worth of assets from the protocol to prevent an imminent hack from occurring. In fact, this hack had been attempted unsuccessfully several times before the funds were rescued. In order to explain the cause of this hack, we first need to describe how ApeCoin staking works in ParaSpace. If you wanted to stake ApeCoin through ParaSpace, you would deposit ApeCoin into the C-Ape contract. What happens here is that when you deposit this ApeCoin into C-Ape, C-Ape actually sends you back some C-Ape tokens. Also, C-Ape is going to stake the ApeCoins you deposited on behalf of itself into the ApeCoin staking contract. Now, C-Ape is part of the ParaSpace protocol. ApeCoin staking is not part of the ParaSpace protocol. So when you stake in the ApeCoin staking contract, you always have to stake on behalf of someone. In this case, C-Ape simply stakes on behalf of itself, and you can think of this as C-Ape staking on behalf of the protocol. What happens in the ApeCoin staking contract when we stake on behalf of C-Ape is that the state is updated to update the staked amount for C-Ape, which is going to increase because of this additional amount that is staked. And this number is going to become quite important later on. So as we mentioned, when users stake ApeCoin into the C-Ape contract, they actually get some C-Ape tokens. And these C-Ape tokens can be deposited back into the ParaSpace protocol to be used as collateral. And then loans can be taken out against the C-Ape collateral. And so it's critical for the protocol to be able to calculate the accurate collateral value of these C-Ape tokens. Now over here is the formula which shows us how to calculate the collateral value of the C-Ape token. And you can see that it's directly proportional to the amount of the staked amount for C-Ape. The staked amount for C-Ape was increased here when C-Ape staked on behalf of itself. So this number is quite important as it directly determines the collateral value of the C-Ape collateral. Now what the hacker did is they staked ApeCoin directly to the ApeCoin staking contract. They did not go through C-Ape, and they also staked on behalf of C-Ape, not on behalf of themselves. So this resulted in the staked amount for C-Ape increasing. This means that this component of the collateral value calculation here also increased, and that the collateral value was inflated over here. Now, because of the inflated collateral value, the hacker was able to take out an under-collateralized loan for ParaSpace and essentially extract funds from the protocol. The first step of this hack was for the attacker to take a large flash loan of WST ETH from Aave. They then supplied some of this WST ETH into ParaSpace as collateral. They then took a loan out in CAPE using that collateral. Now, this CAPE that they borrowed, in step 3, they simply deposited it right back into the protocol to be used as collateral. In step 4, the attacker used some of the WST they retrieved from the flash loan over here and swapped this for ApeCoin using Uniswap. So at this point, the hacker has some WST collateral in ParaSpace, the attacker has some CAPE collateral in ParaSpace, and the attacker has also obtained ApeCoin using Uniswap. The next step here is that the attacker stakes Ape directly to the ApeCoin staking contract on behalf of CAPE. And this results in the collateral value of the CAPE token becoming inflated. And because of this, the attacker is able to take a large loan, much larger than they should be able to take, again from ParaSpace. And this loan is going to be under-collateralized, effectively extracting funds from the protocol. Now, the hacker actually attempted this exploit 3 times unsuccessfully, and various security firms actually noticed this. One security firm decided to front-run the exploit, and they were successfully able to do so and rescue the funds. Now, the ParaSpace team paused the protocol on the day of the hack, and at that point, it's not clear whether they knew the funds had been rescued or if they thought an actual hack had occurred. The ParaSpace team then worked on a fix in collaboration with some security partners, and the fix also underwent an audit before it was deployed. Functionality was opened up in phases. So first, the repay functionality was enabled a few days after the hack, and full functionality was restored about a week after the hack, and at this point, the fix had been both audited and deployed. Also, the team implemented time locks for large withdrawals to potentially stop large hacks from occurring in the future. Now, ParaSpace actually has had 9 audits, but not all 9 audits covered the vulnerable contract in scope. So it's important to realize that not all audits of a protocol cover all components of the protocol. Threat modeling could have helped to analyze which components of the collateral calculations were manipulatable. And in this case, part of this collateral calculation was dependent on the state of the ApeCoin staking contract. The ApeCoin staking contract was not part of ParaSpace, it was an external contract. And so the state within this contract was modified in a way that the protocol did not expect. In these cases, it's better to track state within the protocol contract itself because the state can be modified in a way that is undesirable for the protocol within the ApeCoin staking contract. And this is exactly the fix that was made by ParaSpace. Also, several security firms had tried to contact ParaSpace when they noticed that an attacker was trying to execute this hack. However, they were not able to get in touch with ParaSpace. So it would be a good idea for protocols to have some type of fast communication channel for security firms and researchers to notify them of any potential issues. It would be much preferable for them to stop a hack using some type of pause transaction rather than relying on a security firm to front-run the attack. Front-running the attack has its own risks as well. Another protocol that was exploited in March is Tender.Fi. And Tender.Fi is a lending protocol deployed on Arbitrum. The protocol supports auto-compounding as well as the collateralization of popular DeFi assets including GMX and GLP. GMX is the governance token of the GMX protocol, and GLP is the LP token of GMX. Now, on March 7th, the protocol was exploited due to a misconfigured price feed for GMX tokens, and this happened shortly after a price feed upgrade. Now, the root cause of the hack lay within this GMX price oracle contract. In particular, it was to do with this getGMX price function. This getGMX price function was retrieving the GMX token price from Chainlink. However, it took the result from Chainlink and multiplied it by 1e20, or 10 to the power of 20. This resulted in this function returning a price that was 10 to the power of 20 times larger than it should have been. As a result, the hacker was able to provide just 1 GMX token as collateral and borrow almost all the funds in Tender.Fi. The price feed upgrade happened just 8 hours before the actual exploit. And this just tells us that the attacker was able to detect this vulnerability very quickly after the upgrade happened. The team paused borrowing the protocol about 90 minutes after the exploit, and the hacker sent an on-chain message to the team explaining the root cause of the hack, and the hacker also requested that the team set up a secure communication channel with them. Now, the team negotiated for the return of funds in exchange for giving the hacker 62 ETH as a bug bounty. The Tender.Fi team also created a postmortem, and within the postmortem, it was revealed that the bug might have been missed due to the tests acting upon cached build artifacts, and so the latest code may not have been tested. Also, the bug was written 5 weeks prior to the actual deployment. Now, the best way to prevent an error like this is to have a test which would assert the correct result of this getGMX price function. Ideally, this test would also be operating on some localized fork of the Arbiter mainnet, and that way we're simulating an actual call to the Chainlink contract. Such a test would have easily detected this issue. Also, we want to note here that this function is using a deprecated Chainlink function in order to retrieve the price. The modern way of retrieving price from Chainlink is to use the latest round data function. And the latest round data function will return both the price as well as the timestamp. This lets us validate the timestamp in order to ensure that the price is not stale. We should also ensure that the price returned by Chainlink is greater than 0, just as a sanity check to ensure that something terribly wrong hasn't happened with the price feed. The team also mentioned that part of the issue was the testing may have been operating or executing on a cached build artifact. So it's important to have a robust CI process which will build the latest build artifacts and have the tests execute upon those build artifacts. Another security incident in March was the attempted governance exploit of Swerve Finance. Swerve Finance is a clone of Curve Finance, and it has been inactive since 2021. However, despite being inactive, $1.3 million in stablecoins remains as liquidity in Swerve Finance, and this was the target of the hack. However, the hacker was unsuccessful in executing the exploit. And this ended up being a case where the hacker cooperated with other parties in order to make the governance attack impossible in the future. And they did receive a bounty as well. Now, Spreakaway on Twitter identified the governance attack before it was successfully executed. The attacker created a proposal to transfer Swerve's $1.3 million in liquidity to themselves, but they failed to reach the quorum for passing the proposal. They even tried to coordinate with some other accounts, but failed to do so. What happened next was that Frank Researcher on Twitter was able to dox the attacker through transaction tracing. Once the doxing happened, the attacker decided to cooperate with security firms as well as the community to make the governance attack impossible in the future in exchange for a bug bounty. Now, despite Swerve Finance being inactive for years, the Swerve Finance team retweeted threads on Twitter about the attack for visibility. And the hacker did earn a bug bounty of $93K, however, they were still in the red. And this is because they spent about $140K acquiring governance tokens and a voting power. And while they were doing that, they also were subject to a sandwich attack. The resolution for this problem was that the ownership of the pool was set to the 0 address. So previously, the ownership of the pool was set to the governance address. And so by setting it to the 0 address, all the privileges of the governance contract were removed, and future governance attacks were made impossible. However, normal functionality such as swaps and the addition and removal of liquidity remained. Also in March, an exploit on Hedera temporarily took the whole chain down. Hedera is a proof-of-stake layer 1 with a hashgraph consensus algorithm. Hedera is also an EVM-compatible chain. Now, the hack which occurred was primarily due to precompiled contracts modifying state in an unexpected way. And this hack saw about $600K in stolen funds. The loss could have been worse if not for the intervention by Hedera and other organizations within the community. Now, precompiled contracts execute complex library functions that are not suitable for execution in EVM. If you tried to execute this logic using normal opcodes, it would be incredibly expensive and inefficient. And so precompiled contracts solve this problem by having fixed logic and gas costs. Some examples of precompiled functions include ECRecover and SHA-256 hash. These functions run on the client side for improved performance as well. Now, typically, precompiled contracts don't modify state. However, in cases where precompiled contracts do modify state, it's important to check that there's no delegate call happening, because precompiled contracts work in a different way when modifying state with delegate calls. In order to explain this, let's have a look at an example. Let's suppose we have an EOA here that is calling some function on contract A. When this happens, message sender on contract A is the EOA because the EOA is the caller of contract A. And if any state was to be modified within this function, it would be the storage of contract A that would be modified. Now, contract A makes a delegate call to some contract B, which is a precompiled contract. Since this is a delegate call, message sender remains as the EOA. It will not be contract A. However, if any state changes were to be made here during the execution of this precompiled contract, the state changes would be made to the precompiled contract, not to contract A. Normally, with delegate calls, you would expect the state to change in contract A, but this is not the case when you make a delegate call to a precompiled contract. And so how did the hacker exploit this and profit from it? Well, the hacker first deployed an attack contract over here. Then they called the swap function on some DEX on Hedera, and as part of this call, they provided the attack contract address. And now perhaps the funds were sent to this attack contract and executed and this resulted in the execution of a function on the attack contract. The attack contract then makes a delegate call to a precompiled contract. In fact, this precompiled contract is the Hedera token service. Now, when the call is made from the Uniswap function or the DEX function to the attack contract, message sender is going to be the DEX address. This is because it's the DEX that is calling this attack contract. However, when this delegate call is made to the Hedera token service, the context remains the same. The message sender is still going to be the DEX, right? So this Hedera token service features this approve function, which is like a normal ERC20 approve function. And essentially, in this case, since message sender is DEX, it appears that the DEX is approving some other address to spend all of its tokens. And so the attacker is able to make the DEX approve some address that it controls to spend all of the DEX's tokens. So after this happens, the attacker just uses that account that they control to transfer all the tokens from the DEX into that account. And essentially, the attacker has drained that DEX pool. Now, through the efforts of Hedera and many other organizations within the community, a fix was created for this problem. And as a result of this fix, delegate call could no longer be used to invoke the precompiled contracts, especially with the Hedera token service. Also, previously granted privileges to the hacker, such as those approvals, were removed in the code update. Bridge operators also halted their bridges to prevent the hacker from moving their funds off-chain. Also, as the fix was being developed, access to mainnet was shut down by turning off the network proxies. Essentially, Hedera remained inaccessible while the fix was being developed. The fix was deployed almost 2 days after the hack was discovered. The takeaway from this hack for both auditors and developers is to use caution when precompiled contracts change state, especially if it can happen in an unexpected way. Another hack which occurred in March was on Poolz Finance protocol. Poolz is an IDO platform for new crypto projects, and this hack saw about 665K lost due to a classic integer overflow vulnerability. The attacker basically created a new pool while specifying a very large start amount. However, due to an overflow within the pool, they were able to specify this very large start amount, but still only deposit one token. users began to deploy or to deposit tokens into this pool, and the pool began to grow. Once the pool grew large enough, the creator of the pool, that is the hacker, simply withdrew all the tokens which the other users had deposited. And they were able to do this because it looked as if this hacker had deposited a large amount when they originally created the pool, even though they really hadn't. To prevent overflow vulnerabilities, it's recommended to use a Solidity version that's 0.8 or greater. Also, if using a Solidity version that's older, the Safe math library can be used to prevent overflows. Overflows are also detectable by static analysis tools such as Slither. Another hack which happened in March due to insufficient validation was on the Thunderlands protocol. And the Thunderlands contract could allow anyone to assign the DAO address for the contract. And the DAO address had some special privileges, including the ability to move funds from the contract. So the hacker simply assigned the DAO to a malicious contract which they controlled, and then drained the funds from the Thunderlands protocol. PeopleDao also suffered an exploit in March. However, this exploit had nothing to do with smart contract vulnerabilities. In fact, it simply involved the sneaky use of a Google Sheet. The February accounting Google Sheet was accidentally shared on a public Discord channel, and the sheet was publicly editable. Now, the attacker added a hidden row into the sheet with their own address and specified a transfer of 76 ETH. And the PeopleDao multisig actually approved this transaction, and the transfer was executed for the transfer of 76 ETH from the treasury account to the attacker. Here's a couple of price manipulation hacks which happened in March. First up, we have UNMS. UNMS featured this claim mint function that would allow the minting of UNMS tokens. However, the amount minted depended on the reserve ratio of BUSDT and UNMS. The attacker used a flash swap from PancakeSwap to remove all the BUSD from the pool, and so the reserve ratio was completely skewed at this point. They then called the claim mint function to mint far more UNMS tokens than they should have been able to, and then they dumped these UNMS tokens to make a profit. Then we have Definix on Binance Smart Chain. In the case of Definix, there were several low liquidity pools which the attacker made large swaps on to manipulate the price. Definix also features a rebalance function which anyone can call to force the protocol to rebalance the price. The attacker called this function and then made swaps in the opposite direction in order to make a profit. Let's talk about some of the trends we've seen within these hacks in March. Now, 4 of the largest hacks had the majority of their funds returned. In the case of Euler, almost all the funds were returned. In the case of Safemoon, ParaSpace, and Tender.Fi, almost all the funds were returned, less a bug bounty. And 2 large hacks were blocked by security teams or the community, and this was the case in both ParaSpace and Swerve. Also, 2 of the large hacks resulted in doxing of the hacker. In the case of Euler, this pressured the hacker into returning all the funds. In the case of Swerve, the attacker was pressured into cooperating with various parties to make the government's attack impossible. On-chain messages were often used to negotiate bug bounties. However, there seems to be also a significant off-chain component to these negotiations. In the case of the Euler hacker, many on-chain messages were sent to Euler hacker from users that lost funds. This may have mounted the pressure for the Euler hacker to return these funds. In a trend that we've also seen in February and January, at least 3 of the largest hacks were caused by vulnerabilities introduced by upgrades. And in some of these cases, the upgrade had not been audited. At least 2 of these hacks, which resulted from vulnerabilities introduced in upgrades, happened within 24 hours of the upgrade. And this just indicates that attackers and hackers are monitoring for upgrades, and they're able to often detect these vulnerabilities from upgrades very quickly. And so it's critical to treat these upgrades with a great deal of caution and care. Additional testing could have prevented many of the exploits which happened in March. Invariant testing may have helped detect the bug which Euler had in their donation mechanism. While this bug was missed in the manual audit, fuzz testing or a tool like FlashSyn would have detected the bug. Also, several protocols suffered from access control vulnerabilities where privileged functions were accessible by anyone. This was the case in both Safemoon and Thunderlands, so tests which ensured that unauthorized users are not able to call these privileged functions would have detected this vulnerability. Also, additional scrutiny and testing on interactions with third-party contracts could have prevented several hacks. In the case of ParaSpace, there was an assumption made about the state in an external contract, which was the 8-coin staking contract. And the state was modifiable in a way that the ParaSpace protocol did not expect. And so additional scrutiny on this 8-coin staking contract and how state can be changed within this contract may have helped to detect this vulnerability. Here are a few other trends we've seen in March. The 3 largest hacks were all facilitated by flash loans, and at least 3 lending protocols were exploited in March. We also saw a continuation of a trend which we saw in February, which is the exploitation or the use of emergency or recovery functions to facilitate the hack. This was the case in Euler, where the donate to reserves function was used, and also the case of Safemoon, where the sync function was used to forcefully update the reserves. This brings us to the end of March. Thanks so much for joining us. Here is the preview for the April PAX Roundup, which will include the MEV bot draining exploit, Sushi Swap, Euler Finance, and many more. Congratulations on making this far. For more security content, check out our Twitter at Quantstamp and our YouTube channel, Quantstamp HQ. Thank you.